In this video and in next couple of videos, we'll be looking into the design of reinforced concrete slabs. Slabs are thin, planar horizontal members that take the vertical forces through flexural actions. Slabs are used as floors in buildings and other structures. From construction perspective, slabs can be divided into two types. Cast in situ reinforced concrete slabs are cast at the site. The concrete is poured at the site, whereas the precast slabs are cast at the factory and delivered to the site and are erected at the site. From the functional perspective, slabs can be divided into two types. One is suspended slab and another one is slab on ground. Suspended slabs rest on rectangular grid of beams, walls or columns. They are used to separate the floor from upper space to the lower space. They sustain transverse load, the vertical loads, by flexural actions. Whereas the slab on ground, they rest on the ground and they spread the load to the supporting ground. They provide the working surface as well as they seal the ground as well. The suspended slab can be divided into two types again, one-way slabs and two-way slabs. One-way slab rests on two parallel supports only. The slab can be simply supported or continuous over multiple span. As you can see in the figure here, slab is resting on two parallel supports. That means it will bend in only one direction. There will be significant bending moment only in one direction, as you can see in the figure here. It is bending in one direction. That means you will need to provide the flexural reinforcement at the bottom surface where the tension is in this direction. So as you can see here, the slab is spanning over this direction, so you have to provide the main flexural reinforcement along the direction of span in the tension side, and that is called as a main flexural reinforcement. The secondary reinforcement you have to provide in the vertical direction to the direction of span, mainly to control the cracking due to shrinkage and temperature effects. The other type of suspended slab is two-way slabs. Unlike one-way slab, the two-way slabs rest on beams or columns or walls on all four sides. That means they will have significant flexural moments in both the direction. As you can see here, this slab, the two-way slab, is spanning in both the direction and it is bending over both the direction. That means it has significant bending moment in both the directions. And we have to provide the flexural reinforcements in both the directions. Two-way slabs are stiffer and stronger than one-way slabs and are hence tend to be thinner as well. So wherever is possible, we need to provide two-way slabs because it is thinner and it is more stronger as well. Apart from that, there are other types of slabs as well, as you can see here in the figures. The flat slabs, as you can see here, they are supported only on the columns. There are no beams. As you can see, there are no beams here. They are supported directly on the columns. But to increase the capacity and to resist the punching shear, we provide drop panels or column capitals. As you can see, the column capitals are provided and the drop panels are provided here to improve the capacity and to resist the punching shear in the flat slabs. For the flat plate, as you can see here, there are no drop panels or column capitals. The slab directly rests on the columns. Flat plates and flat slabs are popular because there are no beams in there. That means it has a clear flat surface at the bottom, so you have a more clear working height for the building, and also the formwork is much easier to construct, and also it reduces the construction time as well. However, the drawback is that you have to take a special care so that the column doesn't punch through the slab. Punching shear is a critical failure mechanism in flat slab or flat plates. Another type of slab is a waffle slab, as you can see here. In waffle slab, we have reinforced ribs in both directions, forming a waffle-like pattern, as you can see here. This slab is called as a band beam slab. They are mostly used in car parks that require longer span in one direction compared to the other direction. The composite slabs, on the other hand, uses the light steel decking system as the formwork, permanent formwork, and the slab is cast on it. The hollow core slab, as you can see here, have hollow cores in it, and it helps to reduce the weight of the slab. They are mostly used in the precast slabs. Again, this is another picture of the Waffle slab. As you can see here, the main advantage of Waffle slab is that it can take a large vertical loads, and it looks good as well. However, the formwork for the construction of Waffle slab can be pretty tricky. Band beam slab, as you can see here, used in car park where the slab is longer in one particular direction. Drop panel, as you can see here, drop panels are used to prevent the punching shear effects. So far as analysis of slabs are concerned, slab thickness is much lower compared to its other two directions, the length and width. The thickness is much lower. Hence, the prime stress in the slabs are resulting from the bending moments. So bending moments are the main load effects in the slabs. Slabs do have the torsional moments, transverse shears, and longitudinal forces that act on the slab. However, in the simplified analysis, all the loads are assumed to be transferred to the supports mainly from the normal moments mx and my, and the corresponding shear forces Vx and Vy. And in the simplified analysis, the torsional moments and the membrane forces are ignored. AS3600 prescribes several different ways of analysis of slabs. The first one is a simplified method as shown in class 6.10. And we'll be using this method in this lecture. This method uses a set of coefficients to determine the design moment at critical sections. And also additional provisions are given to control the cracking in the slabs in both one-way and two-way slabs. AS3600 gives following restriction on the application of this simplified method. This method cannot be applied for the design of the buildings that carry significant horizontal forces. For the application of this method, the adjacent spans should be of reasonably uniformly distributed live load acting on the slab must not exceed twice the dead load acting on the slab, and the slab cross section should be uniform. That means the I shouldn't change. Idealized frame method uses an equivalent beam column frame to represent the behavior of the rail structures. As you can see in the figure, in this method the column and the beams are also taken into account to simulate the rail structure behavior. The contribution of the various members to the overall stiffness of the structure are taken into account in this method. Another method is more rigorous structure analysis method using a finite element method. In these methods, concrete slabs are usually treated as elastic plates. Finally, the plastic analysis can also be used for the slab analysis. In this method, yield line method is used to find out the limit states of the slab by considering the yield lines that occur in the slab as a collapse mechanism. From the ultimate strain design perspective, we have to make sure that a slab has adequate capacity in bending. That means design moment capacity phi mu is greater than or equal to the moment m star, and also it has a capacity in shear as well, that is phi vu. The design shear capacity is greater than or equal to v star in both the direction. And if it is a flat slab or flat plates, we have to also do the design check for punching shear as well. That means phi vu, the punching shear capacity, should be greater than or equal to v star. As you can see here, for the flat plates or flat slab where the slab is resting directly on the columns, then the punching shear can be a critical failure mechanism, and a special design capacity check should be done for punching shear as well. From serviceability limit perspective, deflection should not exceed the acceptable values as given in the code. And as you know, the dominant parameter that influences the deflection is the effective depth of the slab. and we have to make sure that the slab has enough effective depth to control the deflection. AS3600 provides 3 different methods for calculating the deflections. The refined calculations as shown in clause 9.4.2, there is a simplified method as shown in clause 9.4.3, and there is also a deemed to comply span to depth ratio for reinforced concrete slab as given in clause 9.4.4, and we'll be looking into the deemed to comply span to depth ratio for the slab design for serviceable limit state. And clause 9.5 deals with the crack control. Mainly from the durability and fire resistance perspective, the size and spacing of the crack must be controlled, and for most of the structures, surface cracks should not be greater than 0.3 millimeter. And the main aim is to promote a large number of smaller cracks rather than a small number of large cracks. So for the slabs, smaller diameter bar, usually in 12 or in 16 diameter bars at closer spacing around 100 to 300 millimeter is preferred. And also we have to provide proper secondary reinforcements to control cracking caused by the shrinkage and the temperature effects as well, as per clause 9.5.3. For deflection control, as mentioned earlier, we'll be using deemed to comply span to depth ratio as mentioned in clause 9.4.4. This method can be used when the live load acting on the slab does not exceed the permanent action, that is the dead load. Deemed to comply span to depth ratio is given in clause 9.4.4. L effective, that is the effective span of the slab over depth, should not be greater than this value, where K3 takes into account the type of the slab, K4 takes into account the support condition, whether it is simply support or continuous support the slab. Delta over L effective here is the maximum deflection allowed as given in table 2.3.2. EC here is the Young's modulus of concrete, and FDEF is the effective design service load per unit area in kilopascals. So if we compute this once, and we can find out what is the effective depth required for the slab, and if this condition is met, then we understand that the slab deflection will be under control.